Okay, so before we were so rudely cut off, a cubic function, domain and range are all real numbers, never changes. When my lead coefficient is positive, my end behavior is down up. Now, this is a much different representation of cubic functions than we studied. Like I was saying, we studied bounce points and cross points, and this one, if the cubic only has one term, oh my gosh, guys, I'm sorry, then my graph is either strictly increasing or strictly decreasing. Okay, let me fix that up. So if k is a negative number, then my end behavior is up, down. So it verifies this graph here. I don't know why I'm having such a hard time with this. Okay. All right, next, equation of a circle. Okay, you may or may not have studied these in Algebra 2 last year. In the circle, I have a center at the point h comma k, and my radius is whatever the square root of r squared is. Okay, so whatever the square root of the number that it's equal to. So let me draw a circle with 1, 2, 3, a radius of 3. Now, depending on where the center is, the domain and range will change. But if you look at this, my domain is my x values, right? So from left to right, my domain is just, it's whatever the width of my radius is, okay? So my range from top to bottom, same deal. Okay, so again, it'll change depending on the center, but if we're looking just like the other ones have a vertex at the origin, if the center's at the origin, my domain and range are directly related to the radius. All right, our square root function. So we know that we can't take the square root of a negative number. So if I'm just looking at my parent function, my domain would be from 0 to infinity. I can take the square root of 0. It is 0, so that is included. Okay, if k is a positive number, then my graph is strictly in my first quadrant. If k is a negative number, like my other graphs, it becomes a reflection over the x-axis. So if k is positive, if my input is positive, my output has to be positive. Again, I can take the square root of 0, so 0 is included in the range. If k is negative, then all my outputs are negative, because think about what it's doing. It's taking a negative number and multiplying it by a positive number. Also, 0 is included. All right, next, our exponential function. Now, we're not talking about the value of a here, but rather the value of b. So the base of our exponent here. If b is positive, then our graph is exponential growth. So as x gets bigger, y gets bigger. If b is a number between 0 and 1, I have exponential decay. So that means as x grows, as x gets bigger, y gets smaller. So now looking at these two graphs, hopefully you can see we have a horizontal asymptote at y is equal to 0. So that's going to be directly related to the range. X is all real numbers, okay, and that'll never change. It doesn't matter if x is positive, negative, a fraction, a decimal, an integer, irrational, rational. We can always plug it into our function and get an output. The outputs, however, notice that my range are all positive numbers. All right, and we do an extensive study on why it can't equal 0. We come back to our exponent rules. But my range, because I have that horizontal asymptote, y can equal 0. And no matter what my input is, all my outputs will be positive. This one's lastly. All right, our floor function. So it looks a little funky. Okay, but the floor function, it rounds down to the greatest integer less than or equal to whatever my input value is. So if we were just to look at a couple examples, if I have 1.2. If I were to take 1.2 and round it down to the closest integer, it would round down to 1. If I had 2, well, 2 is an integer, so I don't have to round down. It would just be equal to 2. If I have negative 0.1, so think of where negative 0.1 is on the number line. It would be pretty close to 0. If you have to take negative 0.1 and round it down to the next closest integer, though, it would be equal to negative 1. Okay? So the graph of this is the step function, which you may or may not have studied when you were studying piecewise functions last year. But I'm going to 1, 2. I'm going to make my scale a half, just so I'm not cramming in the graph. Okay, so if I'm any number between 0 and 1, so even 0.9, I still round that down to 0. So the between 0 and 1, all of these values would round down to 0. The floor function of 0 itself is 0, though. When I get to 1, I can't round down to 1, so that gets an open circle, but the floor function of 1 is equal to 1. So the closed circle goes to where y is equal to 1. Any number between 1 and 2 gets rounded down to 1 until I get to 2. So on this step function, on this floor function, the leftmost x values are always closed and the rightmost x values are always open. Okay, so leftmost are closed, rightmost are open. Same deal when we get into our negatives. Rightmost are open, leftmost are closed, open and closed, open and closed. And then between them, I just connect them with a straight line, because that's telling me wherever I am on this graph, I'm always going to round down to the next integer. So now you can understand why the graph is called a step function. Okay, my domain is all real numbers for this. Never changes. We can plug any number in and round it down. But then the range is a little bit different. Now the range you wouldn't write in interval notation. Hopefully you're thinking to yourself, all right, well, what are my outputs? My y values, my outputs can only be integers. So that's exactly what our range is. Our range is just all integers. Okay? And I won't get into just yet how you would write that. But of all these functions, the floor and the circle are the ones that we would need a little bit more work with. But the other 8, you have to be able to recognize what those graphs, what those parent functions are, and what their domain and range are. Okay, thank you guys.